the next talk by Barvinsky, high derivative quantum gravity, Hořava difference theory, and others. Yes.
Okay, thank you.
Верхняя кнопка это лазер, а влево-вправо это переключение спин.
And I presume I have to speak English, yeah? And how much time would I need?
It's 45 minutes including questions, so please leave 7 minutes for questions.
Yeah,
something like 30
we are getting somewhat
minutes.
late. Okay, let me begin my talk with great thanks for the to the organizers of the conference for this invitation, and moreover for offering the plenary talk, which I definitely do not deserve because you know.
Можете, пожалуйста, микрофон поближе к микрофону?
What is it?
Поближе микрофон.
Okay, because you know, I think that in my talk there will be much more questions than the answers, and the whole subject is more like on methods rather than the concrete results. And you know, the plenary talks are usually supposed to be the ones where you present the material which is very well established and experimentally related, but in my case it will be very different from what I from the previous talks, for example. Anyway, so this talk, work was based on the collaboration with the list of people to whom I'm very grateful for very productive cooperation. And what I will be talking about, basically, this is an attempt to make, to construct quantum gravity theory that would be both local, unitary, renormalizable, and consistent in the high energy limit. And on the way to this goal, there is a lots of obstacles, and some of these obstacles were actually circumvented by using the approach suggested very long by now, actually, more than well, 10 years or even more ago, by borrowing the ideas from solid-state physics. This is the idea of the Lifshitz anisotropic scaling invariance of the theory that was applied by Petr Hořava to the gravitational models. So I will talk, you saw actually the set of questions that I'm going to discuss, and so to say the most interesting part of it may be the statement that in 3 + 1 dimensional, 4-dimensional gravity theory, in principle, one can construct one example of renormalizable and asymptotically free in ultraviolet theory. But of course, there is a number of big questions and problems that stay unresolved. And moreover, if you look at the scope of gravitational theories with high derivatives, then you will observe a number of new questions arising and modifying actually the previous results that were considered to be classical. So let me begin with the discussion of problem of renormalizability of quantum gravity. You know very well that Einstein's theory is not renormalizable in the usual sense, and within the perturbative field theory. But if you add high derivatives, the terms quadratic in the curvature, then this is a very well-known result that it can be done, it can become renormalizable. But unfortunately, and moreover, it was shown to be formally asymptotically free in the ultraviolet limit in the works of Fratkin and Seiting. And however, this theory possesses ghosts. So the kinetic terms of the physical modes, massive graviton, is negative, contributes negatively to the action, and this actually causes a big problem with interpretation of the theory, stability, and so on. So the idea to circumvent this difficulty was due to Hořava, who suggested a very simple thing. Let us replace by higher derivatives only the spatial ones in the Lagrangian. And it would be just enough to make Feynman diagrams of the corresponding quantum corrections better convergent than in the Einstein theory. So in order to somehow cope with the problem of bookkeeping the full set of counter terms, or to make this set of counter terms finite, it was also suggested to exploit the idea coming from solid state physics, the idea of Lifshitz that was suggested by him sometimes in the first part of the last century. The idea to introduce in the theory global symmetry, which is the global symmetry which is called anisotropic scaling invariance. Well, you know, when you replace only spatial derivatives by higher order powers, then of course the theory loses Lorentz invariance. And instead of and in order to get some invariance of this theory, global invariance of this theory, it is necessary to consider the scaling when the spatial coordinates and time coordinates are being rescaled by different powers of one global parameter. And so this idea, actually, if it is applied to local field theory, then it can be very easily shown that this parameter, this power of this parameter z, if it is greater or equal than the spatial dimensionality of this theory, then this theory becomes, can be done renormalizable. And this idea was applied in the case of gravity theory in the framework of the well-known 3+1, or better to say in the general case, D+1 decomposition of full space-time into time and space, and using the so-called ADM variables, Leb's function, three-dimensional, d-dimensional spatial metric, shift functions, and ascribing to these variables different dimensionalities depending on this parameter z, and correspondingly ascribing the dimensionalities to spatial, different dimensionalities to spatial coordinates and to the time coordinate. So it turned out that the structure of the Lagrangian that would be allegedly renormalizable looks as follows. You have the kinetic term constructed out of the quadratic combination of extrinsic curvature, roughly speaking, the time derivative of spatial metric. And also you have the potential term, which is built of the curvature invariance of three-dimensional metric, and this potential term, say in the case of 3+1 dimensional theory, it should include the structures up to the cubic order in spatial curvature, and having the total dimensionality in units of the inverse lengths equal to 6. Then this theory also might have also other invariants included into the structure, which are proportional to the parameter of acceleration, spatial derivatives of the Leb's function. But one can actually disentangle the whole set of possible theories of this type, the so-called projectable subclass, and non-projectable. So in projectable case, which is much simpler, the parameter, the function of the lapse actually is frozen. It's considered to be constant. And on the other hand, the non-projectable one has dynamically active lapse function. So why do I separate these two classes of theories? It will turn out in the end that at the moment we can only guarantee the construction of the renormalizable theory only in the projectable case. Unfortunately, this projectable theory, from the viewpoint of physical applications in the low energy, in the infrared domain, is not successful in the sense of matching with general relativity, with experimentally observable realm that we have around us. The problem is that this theory has physical degrees of freedom. This is a transverse traceless graviton and a scalar, and the distortion relations for these two for these degrees of freedom are given by this expression. So the positivity of this coefficient actually suggests the domain of unitarity of the theory, while which will be unitary and free of tachyon in the high energy domain where the spatial momentum tends to infinity. But in the low energy domain, where you can disregard all high order powers in spatial momenta, there is a big problem. There is a tachyon, whichever sign of the parameter eta you take. Eta is just the coefficient of the three-dimensional curvature, so to say, quasi-Einstein contribution to the total action. So from this viewpoint, this series phenomenologically is useless. But if we consider the only excuse for actually considering this model is that if we disregard the low energy domain and consider the consistency of the unitary of the theory in ultraviolet domain, then we can for a while forget about this low energy limit and consider and just analyze how will it behave in the high energy domain. Well, there is a hope that if you generalize this theory to the case of the non-projectable theory, then according to the paper that is shown here by Diego Blas, Oriol Pusholos, and Sergei Siberikov, then the theory non-projectable Hořava gravity might have also healthy and limit in the infrared domain compatible with Einstein general relativity, including the good behavior, good matching for post-Newtonian coefficients and so on. So with all these reservations, let us do the following. Let us consider just the case of high energies. And for this reason, we will disregard in our construction, the contribution of relevant operators, basically consider only the contribution of marginal operators, and analyze the question of the renormalizability. So how much time do I still have?
So you have 25.
Okay, thank you. Well,
could you keep the microphone closer?
Okay, I'm sorry. Okay, so in a sense, the idea of Hořava Lifshitz to apply the scope of ideas, it was not just the end of the story. To provide real renormalizability of this theory, there has to be, we had to solve a number of rather intriguing problems. And this was done actually in the number of in the papers. And the first problem that has to be solved is to show that a renormalizability of the theory really takes place. And this is not just the question of dimensional considerations. It turned out that in this theory, which violates Lorentzian invariance, the structure of propagators is rather different from the usual Lorentz invariant case. And in order to provide the so-called regularity of these propagators, we had to solve a number of problems, find a special class of gauge conditions in which the proof of renormalizability would go without essential obstacles. Then there was a problem of proving that the set of counter terms can be covariant, that renormalization procedure would not violate the so-called BRST structure of the theory. And this was also shown. And then after this question were resolved for the case of projectable Hořava gravity, then we made several applications, and basically about these applications to the 2+1 dimensional case and 3+1 dimensional that I would be talking about. And in the end, I will show how in 3+1 dimensional situation you can really construct a renormalization group flow from ultraviolet domain to the low energy domain, which would be a kind of a semblance of really Einstein theory in the following sense, that one of the important parameters of this Lagrangian, let me get back and show which one. The parameter lambda here, you see it in the kinetic term. In the Einstein theory, the parameter lambda is just 1. And so we will show that one of the renormalization group flows would be really reaching in the low energy domain this value of lambda or approaching it. And there is a hope that actually the non-projectable generalization of the whole scheme can actually resolve the problem of matching the theory also in the low energy domain with the Einstein gravity, general relativistic gravity theory. So let me now go, basically I will consider these three items of the whole set of problems that have been solved by now. And if I have time in the end, I will actually dwell a little bit on those enigmatic issues in the whole approach associated with the questions which we still do not understand regarding the renormalization group. So, application of all these ideas to two-dimensional toy model of gravity theory looks as follows. Basically, in this 2+1 dimensional case, the structure of the action is rather simple. You have the same kinetic term. Of course, quadratic dependence on first-order derivatives of three-dimensional metric suggests that wave equations of this theory are at most of second order in time derivatives. That's why there is no violation of unitarity, because the unitarity, its violation, is usually related to the presence of higher order derivatives in time variable. But the spatial variables, they are here. They in the quadratic term, quadratic in the Ricci scalar of two-dimensional metric. Then what is important that this theory, its quantum corrections is very well known outside of the mass shell, off-shell, are gauge dependent. But if you restrict the action on mass shell, that means that in the one-loop approximation, say you use just classical equations of motion, then the number of these invariants reduces, and the coefficients of this invariance becomes the so-called essential coupling constant, essential in the terminology of Steven Weinberg. And so it turns out that the coupling constants, essential coupling constants in this case, are just lambda and the dimensionless gravitational coupling constant, which is just the ratio of the original gravitational constant, which is just an overall factor of the whole action, divided by the parameter mu. One should remember that dimensionality in this class of theories is defined not with respect to the physical dimensionality, but the dimensionality associated with that anisotropic scaling which was shown above. So the result of what we did, we just found better functions for this coupling constants, essential coupling constant, a special class of gauge conditions. You see this is a gauge breaking term, as usual it is quadratic in the gauge conditions, and gauge conditions, they have, so to say, quasi-relativistic form. They have time derivatives of the, sorry. Time derivatives of the Lagrange multipliers, which are just shift functions in this Lagrangian, and also spatial derivatives, which are sitting in this term, spatial derivatives of the three-dimensional metric. But in addition, there is a gauge fixing matrix of the special form, which is actually non-local, but its non-locality does not prevent actually the proof of the renormalizability of this local field theory. So the answer for the beta functions are given here, and one can draw renormalization group flows, and in particular these flows, they have sufficiently good properties, asymptotically free ultraviolet fixed point. So this is just a toy model, 2 + 1 dimensions. So what would be much more interesting is to consider how this can be extended to 3 + 1 dimensions. I could just present the results for the beta functions in this case, but I believe that you would like actually to know how these beta functions were calculated. Why? Because you see the problem of this model is the following. The number of coupling constants in this case is much bigger. You know, this time it is 6 essential coupling constants which can be constructed out of 7 coupling constants in the original Lagrangian. And then the question is how to calculate, even in the one loop approximation, these beta functions. This, it turns out that by usual Feynman diagrammatic technique, this is absolutely impossible to do. It is possible to do it by Feynman diagrams only 2 beta functions of the Newton gravitational constant and the beta function of the lambda parameter. And but what about the rest of the beta functions of the rest of the coupling constants? We had to use the method of the first of all background field method by using the so-called background covariant gauge conditions. Then we had to apply the well-known heat kernel method. And finally, we had to use what can be called the dimensional reduction method, which allows this problem to be somehow doable. Well, I don't have time to really explain how the heat kernel method works, but typically this is just the expression of the one loop function determinant of the inverse propagator in terms of the integral over the proper time of the heat kernel of this operator. And for this operator, one can apply the whole machinery of Schwinger-DeWitt technique. And basically, the answer for one-loop divergences of this functional determinant, they express in terms of the so-called Schwinger-DeWitt coefficient, or coefficients, or the coefficients of Gilkey and Seeley, as it is usually formulated in mathematical context. Now, but the problem is that in Hořava gravity, the operators are non-minimal. What does it mean? You see, minimal operator, first of all, it is of second order in derivatives, and its leading term is just the D'Alembertian. But in Hořava gravity, the situation is complicated because the structure of the operators is the following. First of all, of course, the inverse propagator of different degrees of freedom, different fields. It includes, of course, second order time derivatives plus the spatial part. And the spatial part has a structure of 6th order differential operator, which has the following, includes the following combination of terms. And the example, for example, of this operator in the sector of ghost fields and the sector of shift functions is given here. You see how complicated are the structure of contractions of the indices of the covariant derivatives in this operator. You see the indices of covariant derivatives, they are contracted not with each other to form the covariant Laplacian, but they are contracted with the indices of the corresponding fields. And for the metric sector, this structure is even more complicated. So the way how to apply, so this means that the Schwinger-DeWitt technique for minimal operators has to be extended to the class of these non-minimal operators. And this, the idea of this technique is based actually on the notion of the so-called universal functional traces, which is basically, this method is basically equivalent to the expansion in powers of the low derivative part of the corresponding operator and reduction of these corrections to the structures which have the form of the inverse power of the usual D'Alembertian acted upon by covariant derivatives. And the calculation of the divergent parts of these structures can be done by using the usual Schwinger-DeWitt expansion. But that was, again, not enough, because you see the structure of the operator, as you remember, this is not just this complicated non-minimal operator, but there is also the time derivative operator of the second order. And in order to manipulate with this combination, we had to develop the so-called method reduction method. The calculation of beta functions can be actually done on the background which is static in time, but has generic three-dimensional metric. And it turns out that in this situation, the functional determinant of such operator can be expressed in terms of the three-dimensional functional trace of the square root of this operator of the potential spatial derivative part of the operator. And then, of course, there is a question how to extract this square root of this operator of the sixth order in covariant derivatives, which is complicated sixth order differential operator. Perturbatively, this again can be done, and the result is a pseudo differential operator, which is just the infinite expansion infinite series in the structures like this. And these structures are exactly the universal functional traces which I was just describing in the previous slide. So this was the way how all these calculations have been done. You see the complexity of the complexity of the whole problem. In order you would be able to imagine the complexity of the whole problem is the following. If you just try to write down the inverse propagator of the theory in the metric sector, then you would see that it would contain about 200 terms. And the functional determinant of such an operator has to be calculated, its divergent part. And in the usual technique of Feynman diagrams, this would be absolutely impossible because it would be hundreds of millions of individually simple, but there are a number of these structures is so complicated. Anyway, this was done by this method, and the result is presented here. So what do we have? There is a set of essential coupling constant. That's some kind of reparameterization of original coupling constants into some new variables. And for these variables, the set of beta functions is given by this formula. Basically, these are ratios where you have in the numerator the polynomials in the powers of these essential couplings, and there are also some denominators which are given here. Just to give you the notion, the idea of how complicated these polynomials that are standing in the numerator. This is one of them. That's basically, this is the longest one, but you know how many of such polynomials are here. All the results, of course, everything was done by using Wolfram Mathematica, by using the package, exact package on the simple personal computer, personal notebook. And what is the guarantee of the correctness of this result? The guarantee is the following, that it was checked in different gauges, parameterized by parameters sigma and psi. Actually, these are the set of gauges which were shown in the context of 2+1 dimensional model. And it turned out that these beta functions are indeed gauge independent. And this was very strong check. Then also the other verifications have been done based on zeta function regularization, etc. I don't have time to talk about it. Now, question is, how do the renormalization group flows? How much time is it?
You have 7 minutes.
7 minutes? Okay, thank you. So the next step was to find fixed points of these beta functions. And this was done, and again, by using the Grobner basis, the so-called procedure of solving a very complicated set of polynomial equations, we found 4 fixed points and actually proved that there are no other fixed points at finite values of all coupling constants. But it turned out that all renormalization group flows running from these fixed points, which turned out actually all formally asymptotically free, because the number of the sign of the beta function of the gravitational coupling constant, all these points turned out to be negative. So formally they are asymptotically free. But all these flows that would run from this ultraviolet fixed points from them would actually run either to Landau pole, either at finite value of the running scale, or at infinite value deeply in the infrared. So this picture just shows how they look like, but this picture may be not so instructive. What is interesting, that it turned out that from cosmological considerations associated with this this projectable Hořava gravity, it was understood that very interesting domain of this theory is the domain where lambda, the parameter lambda, is infinite. It is interesting from the viewpoint of cosmological applications. And so we decided to check also the presence of fixed points in the hyperplane of lambda tending to infinity. And it turned out that there are also new fixed points, which are actually 8 of them, and 2 of them have very interesting structures. One of them is really asymptotically free. This is the one which is indicated here. with all the values of the coupling constants at this fixed point. And another one, B, is not asymptotically free. And then it turned out that one can find the whole bunch of trajectories, renormalization group equations, which behave as follows. They start in the hyperplane of infinite lambda. They start from the fixed point A. They run into a small vicinity, not exactly, but into a small vicinity of the point B, which is not asymptotically free, but it has one repulsive direction in the transversal to the hyperplane. And from this point, this trajectory runs actually to the domain where lambda is approaching 1. Quite interestingly, the behavior of the gravitational coupling constant G, which actually determines the applicability of the whole formalism, because this is the main coupling constant which determines the magnitude of the interaction in the theory. So it turns out that this G, it is of course, because this is asymptotically asymptotically free, it is 0 in UV, and it turns out to be also 0, tending to 0 in the infrared domain, where lambda tends to 1. And at the intermediate stages, it behaves like this. What this so to say, phase transitions in the behavior of this curve, they actually correspond to this, for example, this one. This is just the point B, where and this point turns out to be the transient point in the renormalization group flow from ultraviolet to infrared. Now, so basically this is the main result. One can say that this is a candidate for really single, known at the moment, local, unitary, renormalizable quantum gravity theory, which is consistent in the ultraviolet domain. But of course there remains a lot of riddles which do not yet have any good resolution. We do not have good answer, for example, regarding the following observation. It turns out, you see, the theory is unitary, and according to the wisdom, conventional folklore wisdom of conformal field theory, the dimensionalities of the operators at the fixed point should be, in such theories, should be real. But it turned out, if you consider the stability matrices at the fixed point, it turns out that very many of them have complex eigenvalues. And it is not clear whether it is a result of the violation of Lorentz invariance, or actually the lack of gauge invariant operators, good definition of gauge invariant operators in such a complicated theory. Because in usual applications of conformal field theory, the assumption of Lorentz invariance is very important. Another interesting and unresolved issue is the issue of, is it really possible to generalize this picture to the case of non-projectable Hořava gravity? There are indications that the contributions of this, so to say, irregular propagators which violate the proof of renormalizability, they actually cancel out. But this still remains an open question which are under study now. But still we hope that if we apply this to non-projectable Hořava gravity, then maybe we would get the model which would not be just a toy example of quantum gravity consistent with Einstein theory in the low energy domain, but it would be a real one. Then the last issue that I wanted to discuss here is a very interesting recent observation due to John Donahue, Roberta Percacci, and their collaborators. That very interesting observation and statement that actually old, by now kind of classical results on the beta functions in usual quadratic gravity theories, which are renormalizable, have asymptotic freedom, that actually this beta function have to be modified. and modified due to a very interesting mechanism. This mechanism is based on the following actually observation. First of all, what does it mean running coupling constant renormalization group approach? In fact, this is much better to formulate as a non-local form factor in the effective action. For example, if you have, say, in electrodynamics, the solution of the renormalization group equation, then this means that simply the term of the effective action can be represented as the bilinear form in the tensor F mu with a non-local kernel of this quadratic form. And this kernel of the quadratic form in the momentum space representation, this is just the function of the running momentum, and this is a running scale. But if you try to apply, for example, this technique to the renormalization of cosmological and gravitational complete constant, then what happens, this interpretation actually breaks down, because we have the situation with a kind of a tadpole structure in the Feynman diagram. Roughly speaking, the external momentum, this momentum P, it actually does not run through the loop. And that's why in the coordinate representation, this is very simple. If you try to, for example, take cosmological term and try to represent it as a non-local form factor acting on something, then it turns out that this non-local form factor as a function of the covariant de Lambertian actually becomes a constant. Similar situation happens in the Einstein term. If you try to replace G by G of box, this non-local form factor, but because if you try to expand the powers of this box operator, then this will be just infinite sequence of total derivative terms, and these total derivative terms after integration over space-time will again generate only constant factor. So there is no notion of this coupling gravitational running gravitational cosmological constants. In quadratic gravity, the considerations of this type also lead to the modification of the notion of the running coupling constant, the coefficient of the quadratic and curvature term.
You have 3 minutes. 3 minutes.
3 minutes?
3 minutes.
Okay, I'm just finishing. Yeah, I think I will skip the last part of the which is very technical, and basically finish with this question. So the
Микрофон повыше. Микрофон повыше.
Why did it? What happened?
Skip last part.
Yes. The system is very clever. Yeah. Okay. So the last item on the agenda of my talk. What was this interesting modification due to the work of Donahue and his co-authors? You see, this suggestion due to them was kind of revolutionary. What they said that the beta function obtained by the usual technique, right, the dimensional regularization or whatever else, but associated with the ultraviolet poles in dimensional regularization. Ultraviolet, this is not the right structure which describes the logarithmic running of quantum corrections. And this statement was based on two mechanisms. One mechanism, I actually already have shown this mechanism. This is a mechanism of tadpoles. But there is another mechanism which is very interesting. For example, if you have this theory with quadratic curvature terms and Einstein term, then the structure of the propagator symbolically has the following form. You have in the denominator q to the fourth plus quadratic in the momentum contribution. And if you consider the Feynman diagrams like bubble diagram of this type, where you have on the external lines sitting the background fields, say second Dodec covariant derivatives of the curvature sitting on the external lines. And here is just a bubble. And if you are calculating everything in the quadratic order approximation in the curvature, then what happens? You have this non-local form factor, which is given sitting between these two structures, is given by this Feynman diagram. And this Feynman diagram is divergent, infrared divergent for m tending to 0. Which means that if you insert this non-zero m back, then you have a logarithmic dependence on the ratio of p squared to m squared. But this is a logarithmic dependence not to the ratio of p squared to mu squared, where mu is the renormalization group parameter of dimensional regularization. But this is a real mass, Planck mass in the Lagrangian modified by Einstein term, modified by the quadratic curvature. And the statement by this group of people is very simple. This logarithmic running is not associated with any ultraviolet divergence, because this integral is infrared, this ultraviolet finite. What happens, interesting? If you calculate this integral, it has the structure 1 over p to the 4th times log. And if you plug it between these two external structures as functions of momentum, then due to Bianchi identities for the Riemann tensor, it happens that these two derivatives, actually 4 derivatives, 2 derivatives here and 2 derivatives here, they can exactly cancel this 1 over p to the 4th structure. And what you have a typically logarithmically running structure quadratic in the curvature. And this is a contribution to the beta function, which is absolutely independent of the ultraviolet divergence. And so this is an open question which has to be understood. I doubt very much that the problem, this mechanism of tadpoles is really working. But this argument seems to be absolutely strict, and there is no doubt that this modification somehow should be taken into account. And this qualitatively changes the conclusions about renormalization group properties of the quadratic gravity theory. So this is what I can't say anything else about this interesting observation. Basically, I think I will stop here. My last section of my talk was about the running of lambda and g. But I would prefer not to talk, because really it is impossible, because it is rather technical, and I don't think that it would be helpful, useful to discuss it now in view of the lack of time. So I just get to my conclusions, which is basically the following. Probably, apparently, what we have now is just a single known now example of local unitary renormalizable and asymptotically free and consistent in UV limit quantum gravity. This is projectable Hořava gravity. And this is the way how salvation of unitarity takes place in local, in models with Lorentz invariance violation. Then it's interesting that there is a toy model which demonstrates asymptotic freedom into +1 case, and the calculation of beta functions and their application shows that in 3+1 dimensions also we have interesting bunch of trajectories representing asymptotically free flow from UV domain to quasi-Einstein general relativistic limit. Thank you very much.
Thank you. These questions?
This problem with tadpole you mentioned, I don't know if you What about 1 plus 2 dimension? Do you have the same problem there?
What about where?
In 1 plus 2 dimension.
In 2 plus 1?
Yeah,
Well,
okay. I wrote the same type of...
I think that roughly speaking, in the UV domain, which is the only domain where we can consider this at the moment, and where it does make sense, you don't see really their infrared divergence, because the origin of this phenomenon is due to the fact that you have with the mass of the Einstein term, the Planck mass switched off, you have infrared divergences. In these models, you don't have this phenomenon, or at least we hope that we don't have this phenomenon. Therefore, it is likely that these results will not be changed by this modification. But I think that the problem with this Lorentz invariant quadratic gravity theory is more important, because this is, so to say, it's more classical result. Who knows really how our world is arranged, whether it is Lorentz invariant or not. After all, Lorentz invariance of our theory, of our nature, is also very conceptually ununderstood fact. So maybe indeed there is a region of energies, but it should be viable. It should be.
Thank you. What is expected for black holes in such models, especially concerning unitarity problem?
It's a good question. I would say rhetorical nature. Hard to say. I don't know. You see, the behavior, in principle, the concept of black holes in Hořava gravity models is conceptually different from the similar concept in Lorentz invariant series, because you see there is a distinguished foliation of space-time, and nevertheless it is possible really to determine solutions which would mimic black holes, and as far as I know, Sergei Siderikov, with his co-author, at a certain point he considered the construction of the horizon in these solutions. So from the viewpoint of qualitatively, the predictions are basically the same, but this is not completely
It is more complicated. There are several special surfaces, not just one horizon.
Several horizons.
They call it Sranov.
Yeah. Actually, you see this. They suggested the formulation of this Hořava gravity model in terms of basically Einstein gravity theory plus Hronon field, and one can treat this Hronon field as just extra matter field on top of Einstein theory, and the causal properties of this Hronon field, they are of course very different, because they are responsible for this violation. But otherwise you can basically treat the whole problem as Einstein equations with a non-trivial matter sources, and these matter sources
This extra piece of beta function Donoghue found, will it also appear, for example, in Born-Infeld electrodynamics?
in where?
Born-Infeld electrodynamics, non-linear electrodynamics.
Look, it depends what do you understand on under nonlinear electrodynamics. If it is already effective theory, well, electrodynamics, you don't have this infrared divergence mechanism. So maybe not. Maybe not.
I have one question. You mentioned that there is a problem with gauge invariance. Can you comment about it? Because I know the Lorentz invariance is violated, but gauge invariance, we want to keep the charge conservation in the theory.
No, because the gauge invariance, you see, there are different things. One thing is violation of gauge invariance, and another is gauge independence. So what actually do you mean? Because gauge independence, this notion is applied basically to any non-abelian gauge theory in the following sense, that if you consider the expectation value of the parameter of physical observable, which is gauge invariant, then it is gauge independent. But for example, effective action, it is not gauge independent of shell, because its variation is respect to the variation of gauge conditions is proportional to effective equation of motion. So if you are outside, then you get uncontrollable in the sense dependence.
So this kind of technical questions. So the technical issue, you cannot construct the structures which are gauge independent.
Conceptually, this is equivalent to the statement, to such a simple statement. If you have the expectation value of the function of the operator does not coincide with the function of the expectation value, and this is a universal statement. But there were examples, are actually approaches where the people tried to construct gauge independent of shell extension. It was the so-called suggestion by Barvinsky and David very long ago, that you can covariantize and make gauge invariant is so strong in the generating function that with this definition you can construct such kind of gauge independent of shell extension for the effective action also of shell. You see? And but there are problems with this method because, roughly speaking, the topological structure of Feynman diagrams generating this one particular reducible Feynman diagrams are irreducible. And therefore, the procedure, for example, of renormalization of this extended effective action does not satisfy the usual rules of R operation. You see it on what happens. And this, as far as I know, this problem has not been resolved. Maybe there is no point to resolve such.
Thank you.
Sorry for my naive question, but I don't understand it correctly. Is it possible to explain standard observational tests for gravity using these models, like a solar system and binary pulsars? Thank you.
I'm afraid this is far beyond what I can say about the application of this model. You see, this is very Maybe I misunderstood the question.
Спрашивает, как можно это на стандартных технических источниках.
One thing for sure, that at the moment we don't have any single confirmation of this Lorentz violation of the theory, because what is it? The difference in the speed of light and speed of gravity is about 10 to the minus 15. So the only, if we still believe in this Lorentz non-invariant theory, then we have to believe that actually the phenomenon of this radiation from this binary system took place at a much lower energy scale, where all these corrections are unimportant. This is the only. But deeply in UV, of course, there might be some deviations which we do not have.
Excuse me, I have a question.
Yeah, thank you for the for the talk. I have two short questions. The first one is, can this theory explain inflation or the stage? And the second question is the long-range behavior of gravity modified in this theory such that we can explain dark matter or dark energy, for example? Thank you.
About dark matter, definitely I can't say anything interesting, and I don't think that it is directly related. But of course, would somehow modify the setting. And regarding the cosmological applications, I know that Hořava gravity was considered in cosmological context. For example, there were works by such people like Mukakiyama and his co-authors, where, for example, he considered the application to the problem of initial conditions, quantum initial conditions for the universe. For example, and of course, quantum state of the universe, this is a question of the origin of inflation. So in this sense, yes. I don't think that I can give you more details about it, but basically this is...
Okay, thank you very much for our time. Thanks to all the speakers.
Thank you.